Welcome, ladies and gentlemen, to the next chapter of the Introduction to Mathematics course. Today I'm going to talk about miscellaneous subjects like combinatorics, sums, and numeral systems. The material I cover in this lecture is just something that did not fit anywhere else, but I think it's important to know these subjects, and so I will just present them here. The different topics we'll be talking about will be sums and products at first. So we introduce the summation and the product symbol. Then we will learn some very basic combinatorics that we use every day in mathematics. We will learn about the binomial sum and the geometric series. And finally, I will introduce different numeral systems. And a thing that you might need to take care of right now is to like this video and subscribe to my channel. Let's begin with sums and products. So we have already encountered sums of the form a1 plus a2 and plus an, where we add a finite number of elements from some sequence, but it's not necessarily specified how many elements we add, so that's why I use the index n here. So it, depending on the situation, could be a different amount of elements we add. And for this we have a convenient notation which makes this a bit more concise, and we use the summation symbol for this. So instead of writing a1 plus a2 plus plus an, we write sum from I equal to 1 to n over ai. The summation symbol is actually the capital Greek sigma. And computer scientists may think of this symbol here as realizing a for loop. So in this for loop, we first initialize the sum with the value 0, and then we run the loop for I from 1 to n, where in each iteration we add the already obtained value of the sum plus ai. And ai would be some array in this fictional programming language here that contains the elements in this number sequence. If the sum is empty, that is, if we sum over 0 elements, then we define the sum to be 0. So that would look like this. If we sum from I equal to 1 to 0, so then the upper index is actually lower than the initial index, then we don't sum over anything and we define this to be 0. And there are some variations to this summation notation. We will not always start at index 1 or end at index n, or we can sum over elements that are functions of the AI, and so it is possible to find expressions such as these. So here we start at a different index than 1. Here the end index is not n, but some expression depending on n, and we don't sum precisely over ai, but over the squared ai, so a function of the ai. Again, here we have some terminal index depending on n, but not being exactly n. And here we shifted the indices in the sum, actually. And yeah, this one here you can equivalently rewrite as summing from I equal to 1 to 2n minus 3 over ai. So if you just write out the individual summands here, beginning at I equal to 3, then you have a3 minus 2, so that would be a1. The next one would be I equal to 4, so it would be a4 minus 2, so it would be a2, and so on. And that's the same in this sum. You begin at a1 because you start at I equal to 1, then the next one would be I equal to 2, which would be a2, and so on. So these two expressions mean the same thing. And if we sum over elements from a finite set A without explicitly enumerating the elements, then we can write it like this. Sum over element A in the set big A, and then we just write A for this a placeholder for all the elements in the set big A. And eventually in your mathematical journey you will encounter infinite sums, but what an infinite sum means depends on the context. So you have to interpret such an expression in the correct way. So this would look like this: sum from I equal to 0 to infinity over the AI. So here you would have an infinite sequence of numbers, countably infinite sequence, so A0, A1, A2, A3, and so on. And sometimes you even have these doubly infinite sums. So you sum from minus infinity to plus infinity, and here you would sum over a sequence where the indices really run over all the integers and not just the natural numbers. And when you encounter such an expression with an infinite sum, then usually it involves some kind of convergence question that is treated in analysis. Similar to the summation symbol, we can also write products. So when we want to multiply elements A1 times A2 times AN, we can conveniently write this as product from I equal to 1 to n over the elements AI. And the product symbol is the capital Greek pi. It actually looks quite similar to the little Greek pi. And again, computer scientists can think of this as a for loop. Here the product is initialized with the value 1, and then we run the loop from 1 to n and multiply the already obtained product with the next element in the number sequence. And the empty product is set to be 1 by definition. So if the upper index is lower than the initial index, then we don't have any elements to multiply with, and we define this to be 1. And as for the summation, there are variations for the product symbol. So for example here, the product over the elements of a set, then we write product A, where A is in the set big A. Or again, it could happen that we don't start at index 1, and the upper index is not just n, but some expression involving n. And again, infinite products are also possible, and of course here also it depends on the context to fill these expressions with some meaning. So again, usually this is some convergence question. Some very basic properties of the sum and product symbol, which you can check by writing these out as the sequences explicitly. So I have two sequences, A1 to AN and B1 to BN, and I just for convenience assume that both sequences have the same amount of elements. For if they didn't, then I could just fill up the shorter sequence with some additional 0 elements or 1 elements for the product. And then I could just take these. So the sum from I equal to 1 to n over AI plus BI is the same as first summing all the AIs, then summing all the BIs and adding these two sums together. And similar for the products, the product from I equal to 1 to n of AI times BI is the same as the product over the AIs multiplied with the product over the BIs. For a fixed number lambda, we have lambda times the sum over the A's is equal to the sum over lambda times the AIs. So this is just the distributive law of the real numbers. And similarly, for the products, if we have the product over the AIs and we take the power to the power of lambda, then we could just as well first take every single AI to the power of lambda and then take the product of those. Next, we're looking into some basic combinatorics. By combinatorics, we mean that part of mathematics that is concerned with counting things or how to count things. And this is really a vast field. But here I only want to introduce a couple of famous counting formulas that are frequently used. First, we need to know what a permutation is. So a permutation of the numbers 1 to n is a bijective map, which I call sigma, from the set of the numbers 1 to n to itself. What this means is that a permutation takes the numbers 1 to n and rearranges them in a different order, namely in the order sigma 1, sigma 2, sigma n. So yeah, we think of this in position 1. We have the image of the element 1 under the map sigma. In position 2, we have the image of the element 2 under sigma, and so on. And often we write this in the following form. We take the numbers 1 to n in the top row, and then underneath we write the corresponding images where the permutation moves them. So when we rearrange the numbers from 1 to n, we have n choices for the position where we want to move 1. So n choices for sigma 1. And once we've fixed this position, so we fix sigma 1, then we are left with n minus 1 choices where we want to move the number 2. So n minus 1 choices for sigma 2. Once we've fixed those two, there are n minus 2 choices for sigma 3. And once we've fixed sigma 1 to sigma 3, we just go on like that, getting one fewer choice in each step. So eventually there are 2 choices where we can place the next to last number n minus 1. And once we've fixed the positions for 1 up to n minus 1, we are left with only one choice where we can move the last number n. So the value for sigma n. I illustrate this here in this little tree where we have the numbers 1, 2, 3, 4, so n equal to 4. And each level in the tree indicates one choice we make here. So first we choose which number gets placed in position 1. So this is the first level of the tree. For example, if we say we put 2 in position 1, so that means sigma 1 equals 2, then the 2 is out. So we're left with the numbers 1, 3, and 4. Now in the second level, in the second step, we ask to which position will we move the number 2. So we could move it to 1, to 3, or to 4. Let's say we move it to position 3. Then the 3 is out, and we're left with the choice of 1 or 4 where we put the third element. So let's say we put number 3 on the element 1. Then we're here, so we've moved down this path here. And now the last step, the fourth choice we make, is where we put the element 4, but the only place left is 4 itself, so the element 4 is moved to itself. So it gets fixed by this particular permutation. And you see this tree here shows all possible permutations of the numbers 1 to 4. And yeah, this illustrates these choices, the decreasing number of choices, quite well. So we begin with 4 choices for the first number, then we have, no matter what we choose, we have 3 choices for the second number. And then again, no matter how we've chosen so far, we always have 2 choices for the third number. And once we've picked the third number, there's always only one choice left. And to facilitate this, we introduced the notation of the factorials. So we write n exclamation mark, which we read as n factorial, to be the number n times n minus 1 times n minus 2 times 2 times 1. And we define 0 factorial to be equal to 1. And what we've seen by the explanation before, that there are n factorial different permutations for the numbers from 1 to n. Okay, to clarify this again, just take a good look at this tree here, or the reasoning we had on the previous slide. Next, we look at certain standard ways of choosing k elements from a set of n elements. And this is a process which is commonly referred to as sampling. And there are different ways to do this. So first we have to distinguish whether the sequence of elements that we choose is ordered or not ordered. So this essentially means we can distinguish between the elements that we pick, or we cannot distinguish. And it makes a difference whether each element can be picked at most once or more than once. So you could imagine if you have a set and you kind of physically take out an element, then you can take it only once. But if you just mark it down somehow, you could do that more than once. So this makes a difference in how we count these possible sampling choices. And often we use some mental model to visualize these sampling ideas. For example, we can think of an urn containing n balls, out of which we can pick k, one after another. And depending on the sampling model that we use, we could think of these balls as being distinguishable or indistinguishable. For example, if all balls look the same, they're indistinguishable, but if the balls have numbers on them or are all in different colors or something like that, they would be distinguishable. And it will also differ in whether we can put a ball back after each pick or we cannot do that. Or an equivalent but somewhat different mental model is that we think of n boxes in which we can place k objects one after another. And depending on which model we choose here, these objects that we place can be distinguishable or indistinguishable, and the boxes could be used more than once or not more than once. So, for example, it could be that once we've put one object in a box, then we cannot reuse this box for another object, or maybe we could place more than one object in that box. So let's go through the different possibilities of the samplings. So first, I look at ordered samples where each element can be picked at most once. So once we take an element out, we cannot choose it again. Here I have 4 elements and I pick 2 of them. So for the first pick, I have 4 options, 1, 2, 3, 4. And then depending on which element I picked in the first one, I have 3 choices for the second pick. So this is actually very similar to what I just reasoned for the permutations. And indeed, we use the same kind of reasoning, only with the permutations we had to go all the way until we had only one choice left, and here we don't have to do this. So we have n choices for the first pick. Once we picked a number, say for example 1, then we have 2, 3 and 4 left to pick. So we have 3 choices, so n minus 1 choices for the second pick. And once we made the first and second pick, there are, if we continue like this, n minus k plus 1 choices for the kth pick. Okay, so think about it, in every step we get 1 fewer choice, and if we do this k times, we're left with n minus k plus 1 choices. And then we are done. Then we stop, because we only pick k elements. So, by this reasoning, we have the following result. There are n times n minus 1 times n minus 2 times n minus k plus 1 possibilities to pick in an ordered way k out of n elements, such that each element can be chosen only once. And with our factorial notation, we can conveniently write this expression as n factorial divided by n minus k factorial. Okay, think about it. N minus k factorial would be the same product starting like this, but then going on with the following factors down to factor 3 times 2 times 1. And to cancel out these additional factors that n factorial would bring in to this expression, we just divide by the product of all of these additional factors, and that is precisely n minus k factorial. Now we look at ordered sample, but where each element can be picked more than once. So we can replace the elements once we pick them. Here again, with 4 elements, I can pick 1 out of 4, but regardless of which one I can pick the same 4 ones again in the second step. So we have n choices for the first pick, and once we pick, there are again n choices for the second pick, and once we've made the first 2 picks, there are again n choices up to the kth pick, and we're done. And what this means is that there are n times n times n times n equal to n to the power of k ordered ways to pick k out of n elements when we can pick each element more than once. So now we look at unordered samples where each element can be picked at most once. And yeah, here we have the following situation. We can pick 4 elements in the first step and then 3 elements in the second step, but we have different ways of picking equivalent paths. So if we pick 1 first and then 3, that's to be considered the same as picking 3 first and then 1. So these 2 paths here are actually just one choice, one possibility for an unordered sample. So we somehow have to get rid of the order in these different paths. Now, to count the unordered choices of k elements, we take all the ordered choices of k elements, which by theorem 3 we have seen to be n factorial divided by n minus k factorial. And then for each of these choices which contain the same elements along the path, there are k factorial ordered choices because we can permute the elements in each of these paths. So we see here we have 1, 3, here we have 3, 1. So this one is just a permutation of this one. So we have k factorial ordered choices that lead to the same k elements. So for the unordered choice of k elements, we have to identify all of these k factorial ordered choices that correspond to it, so that all the ordered choices that contain these k elements. And we do this by taking the number of ordered choices here and divide it by the number of all the choices in here that lead to the same unordered sequence. And this means there are so n factorial divided by k factorial times n minus k factorial unordered ways to pick k out of n elements, such that we can choose each element at most once. And for this we introduce a new notation. So for k between 0 and n, we introduce this binomial coefficient n over k, which is by definition equal to n factorial divided by k factorial times n minus k factorial. And yeah, we read this as n over k. And with this notation we could rephrase theorem 5 as saying there are n over k unordered ways to pick k out of n elements, such that each element can be chosen at most once. Now we come to the tricky one. This is probably the most difficult of all these sampling methods. We look at unordered samples where each element can be picked more than once. So here I have 2 different samples indicated. So the first one is we pick 1, 1, 1. So we pick the element 1 3 times. And the second one is where we pick 2, 2, 1. So we pick the element 2 twice and the element 1 once. But because we're not looking at the order, all the red ones here are actually to be considered equivalent. So it doesn't matter if we have 2, 2, 1, or if we have 2, 1, 2, or if we have 1, 2, 2. So all the red options here should be counted as only one possibility. But this is more complicated than before, because since we allow replacements, different unordered choices can correspond to different numbers of ordered choices. For example, if we pick 3 times the 1, then we have only one path here. But if we pick 2 twice and 1 once, then we have 3 paths which realize this combination of numbers. So we cannot simply take the total number of ordered choices, which would be n to the power of k, and divide out the number of ordered choices for each unordered choice, because there is no single such number. So what we did in the previous case, where we had unordered samples but could pick only once, this doesn't work here. So we need to do something more ingenious. And the idea is now to reduce the case of k unordered choices with replacement, so this one here, to a case that we already know. And we want to reduce it to the case of k unordered choices without replacement, but from a set containing n plus k minus n elements. Now this may be a bit mysterious, but I will show you how to do this, how we can reduce counting these options to counting the options here. And for this case here, we already know the number from the previous theorem. Unordered choices without replacement, we already covered that. So if we can reduce this problem here to one that we already know, then we have our solution. How do we do this? So first I write x index n for the set that contains the numbers from 1 to n. And this is bijective to any other set with n elements, so I just use this set to stand in for our sampling set. Now each unordered sample, where each element from xn can be picked more than once, can be uniquely represented by a k-tuple in the following set A. This is a k-tuple, so each entry here in this tuple stands for one pick, x1 to xk, from the Cartesian product of xn with itself, k times, and we assume that x1 is less or equal to x2, which is less or equal to the next object, up to them being less or equal to xk. So if I have an unordered sample of elements from xn, I might as well arrange the elements in the sample in such a way that the lowest elements come first, then the next lowest elements, and up to the highest elements. And I have less or equal here because I can pick more than once, so it's possible that I pick the same element multiple times. So it could appear that x1 is equal to x2 because I picked it twice, and so on. Okay, and so since I can represent every unordered sample with repeated picking of elements by such an object, the number of the elements in A will be the number we're looking for, the number of unordered samples where I can pick more than once. And also every unordered sample from elements of the set xn plus k minus 1 that can be picked at most once can be uniquely identified with a k-tuple of the set A star. So we have elements x1 star up to xk star, where we require that x1 is strictly less than x2, and so on. So I pick the unordered sample from the numbers from 1 to n plus k minus 1. And because I do not replace the numbers, each number in the sample can appear only once, and then I might as well order them by increasing size, and that would give me precisely such a tuple here with this property. And here I have a strict inequality, is strictly less, because, as I said, any element can appear only once at most. So there's no possibility that there are two identical elements in this sequence. Now we have the following lemma. There exists a bijective map F from the set A to the set A star that maps any k tuple of numbers x1 to xk with this property here to a k tuple of numbers x1 star to xk star with this property here. And this map is given by the entry xi star here is defined to be xi taken from here, plus I minus 1. And of course we need to prove this, and admittedly the proof is a bit tricky. Okay, so here as a reminder the definition of the two sets and the statement of our lemma. And for the proof we first need to verify that the image of this map defined by this formula here is indeed an element of A star. So we need to make sure that every entry that is obtained in this way is first less or equal to n plus k minus 1, and then we need to make sure that they're all strictly ordered in strictly ascending way. Okay, so since xi is less or equal to n for all the xi's in the set xn, we have that xi star, defined by this, is less or equal to n plus I minus 1, because if it's defined like this part is less or equal to n. So xi star is less or equal n plus I minus 1. And we have the maximal index k, so we can say that this is less or equal to n plus k minus 1, because I is less or equal k. And this means xi star is less or equal n plus k minus 1, and hence xi star is an element of x index n plus k minus 1. So that's good. Now we need to verify that the xi stars are really ordered strictly. So we have xi star by definition equal to xi plus I minus 1. Xi is, because it's from the set A, less or equal xi plus 1. So this is less or equal xi plus 1 plus I minus 1. And this is strictly less than xi plus 1 plus I. Okay, so I just drop the minus 1 here, and then this is strictly larger than that. But this is by definition nothing else but xi plus 1 star. So indeed, I've seen that xi star is strictly less than xi plus 1 star for all indices ranging from 1 to k minus 1. So we have proved now that f of x to xk is indeed an element of A star. Next, we will show that f is in fact a bijective map. And we do this by stating an inverse map, f to the minus 1 for f. And we know that if a map has an inverse map, then it is bijective. And we define the inverse map by taking as input a sequence x1 star to xk star and mapping it to a sequence in A, where the entries are given by xi being equal to xi star minus I plus 1 for I from 1 to k. And now you can immediately see that this reverses the effect that our original map f had. So if xi star was obtained originally from such a tuple here that got plugged into f, then we see immediately that we get the original tuple x1 to xk back by applying f to the minus 1. But indeed we need to confirm that f to the minus 1 really maps any given tuple x1 star to xk star into the set A, and does not maybe give us something outside of the set A, because then it would not be a proper inverse map. Now we have that xi star minus I plus 1, so this one here, which is just the image xi in the ith component, lies between 1 and n, because xi star is strictly greater than x1 star because it's from the set A star, and x1 star is strictly greater than 1 because all the starred elements are taken from the set xn plus k minus 1, so they're all elements between 1 and n plus k minus 1. Now, each element in the sequence is strictly greater than the one before it, and between x1 star and xi star there are I minus 1 elements. So if I subtract I minus 1 from xi star, then I'm still greater or equal to x1 star, and x1 star is greater or equal to 1. So here I have this expression xi star minus I plus 1. So that's subtracting I minus 1 from xi star, and this is still greater than x1 star, which in turn is greater or equal to 1. And by a similar argument, we can reason that this expression here is less or equal to n, because there are k minus I elements between xi star and xk star, each of them being strictly greater than the previous one. So xk star is at least by k minus I greater than xi star. And on the other hand, coming from the set xn plus k minus 1, xk star is less or equal to n plus k minus 1. So that means xi star is less or equal to n plus k minus 1 minus k minus I. And if I subtract minus I plus 1 from that, then I get that it's actually less or equal to n. And so we've shown that the components xi in the image of f to the minus 1 are indeed between 1 and n, so they're all contained in the set xn. That's good so far. And now we also need to check that they satisfy this inequality here. So we have xi, which by definition now is xi star minus I plus 1. We know that xi star is strictly less than xi star plus 1. And so it's at least 1 less. So this whole expression here is less or equal to xi plus 1 star minus I. And this we can write as xi plus 1 star minus I plus 1 plus 1. But this by definition is nothing else but xi plus 1 under this formula here. So we have found that xi is less or equal xi plus 1. So indeed, f to the minus 1 maps any tuple x1 star to xk star from the set A star into the set A. And so it's a well-defined inverse map for f. And this shows that f is bijective, and indeed we have a bijection between these two sets A and A star. Now, we use this to show that the cardinality of the set A, as defined here, is the same as the cardinality of the set A star. And by theorem 5, we know that the cardinality of A star is n plus k minus 1 over k. Because, the unordered samples of n plus k minus 1 elements, where we can pick each at most once, that was covered in theorem 5, is given by this binomial coefficient here. And because this set is bijective to this one, and the number of elements in this set correspond to the unordered samples where we can pick each element more than once, we have the following theorem. There are n plus k minus 1 over k unordered ways to pick k out of n elements, such that each element can be chosen more than once. And I summarize this in this table here. So for the ordered samplings with repetition, we have n to the power of k, and without repetition, we have n factorial divided by n minus k factorial. And for the unordered samplings, With repetition, as we just saw, we have n plus k minus 1 over k possibilities, and without repetition we have n over k possibilities. And because binomial coefficients appear so frequently all over mathematics, I want to prove some of their more important properties for future use. So this one here, I'm actually not going to prove it because it's completely obvious from the defining formula. N over 0 is equal to n over n, and both are equal to 1. N over 1 is the same as n over n minus 1, and that's equal to n. And for any index k between 0 and n, we have that n over k is equal to n over n minus k. And yeah, all of these are immediate from this formula here. And there's an easy recursive way to compute the binomial coefficients. It's called Pascal's triangle. So you arrange the binomial coefficients in this order. So in the first line you start with 0 over 0, then in the next line you have 1 over 0, 1 over 1, then in the third line you have 2 over 0, 2 over 1, 2 over 2, then 3 over 0, 3 over 1, 3 over 2, 3 over 3. And here I computed them explicitly, and yeah, this goes on to infinity, and you can get every entry here by adding the ones in the row above it immediately to the left and immediately to the right. Okay, so look at these arrows. So you take the two where the arrows point and you add those two and you get the corresponding entry in the triangle. And we're going to prove this. So it's explicitly written out, this formula. So for k between 1 and n, we have n plus 1 over k equal to n over k minus 1 plus n over k. And for the proof, we first note that for any number m greater or equal to 0, we can write m plus 1 factorial as m plus 1 times m factorial. That's immediately clear from the definition of the factorials, but it's helpful to keep this in mind for the following. And yeah, I denote this by this star to refer back to it later. Now, we have the right-hand side, if we write it out explicitly, n over k minus 1 plus n over k. So this one becomes n factorial over k minus 1 factorial times n minus k plus 1 factorial. And this one becomes n factorial divided by k factorial times n minus k factorial. Now, I do the following. I want to bring them on the same denominator, so I can add these two fractions here. And what I do, I multiply this expression by 1, but I write this one as k divided by k. So I get a factor k in the numerator and I get a factor k in the denominator. And this k multiplied with k minus 1 factorial yields k factorial. So that's the same as here. And for this one, to get the same denominator as here, I multiply by n minus k plus 1 in the numerator and in the denominator. So again, I multiply by 1, but I write it as n minus k plus 1 divided by n minus k plus 1. And again, applying star, I then get n factorial times n minus k plus 1 divided by k factorial times n minus k plus 1 factorial. So we have the same denominators here, so we can just add the numerators. And what I get is n factorial times k plus n minus k plus 1 divided by k factorial times n minus k plus 1 factorial. Okay, now the k here cancels out with the minus k here. So I'm left with n factorial times n plus 1, which again by star is n plus 1 factorial. But now this expression is precisely n plus 1 over k. And this proves our formula for Pascal's triangle. And as an exercise for you, pause the video for a few minutes and prove that if X is a set with n elements, then there are n over k subsets of X that contain k elements, where k runs from 0 to n. Okay, so if you think about it, elements in sets are not ordered and do not appear multiple times. So choosing a subset of X with k elements amounts to choosing k unordered elements from X without repetition. And by our theorem 5, these are n over k possible subsets that we obtain by doing this. Next, we will learn about the binomial sum using some of the combinatorics we have learned before. Now from school you should remember this formula, the binomial formula for the square of the sum of two numbers a and b. So a plus b squared equals a squared plus 2ab plus b squared. And now we're interested in what a formula for higher exponents in the natural numbers would look like. So can we get a formula for a plus b to the power of n? And first we just compute some of these explicitly for lower numbers n up to 4. So here for n equal to 0, of course, we just get 1. For n equal to 1, we just get a plus b. N equal 2, we have the familiar formula from school. Now for n equal to 3, we get this one, a to the power of 3 plus 3 times a squared times b plus 3 times a times b squared plus b to the power of 3. And for n equal to 4, we get a to the power of 4 plus 4 times a to the power of 3 times b plus 6 times a squared b squared plus 4 times a b to the power of 3 plus b to the power of 4. And if we write them in this way, that we put the highest exponents for a on the left and then sort the terms by decreasing the exponent of a and increasing the exponent of b, then we see a certain pattern here for the coefficients that appear with these terms. And that pattern looks quite familiar because it's just Pascal's triangle. So we suspect that if we find a formula for arbitrary numbers n, that we can obtain these coefficients here by taking Pascal's triangle. And that is indeed true. And this is the so-called binomial sum formula. So for two real numbers a and b and some natural number n, we have that a plus b to the power of n equals the sum from k equal to 0 to n of n over k times a to the power of n minus k times b to the power of k. And the proof is a bit of work, so concentrate carefully when we are going through it. We have to work a lot with this summation sign, and it's a good exercise if you're not familiar with it, but also maybe a bit difficult when you see it for the first time. Now we will prove this by induction on n. And first I want to make you aware of the following rule to manipulate sums, which is called an index shift. So if we have a sum from k equal to 0 to n of some expression s where k plus 1 appears in the expression, so it depends on k plus 1, then we can rewrite this as the sum from k equal to 1 to n plus 1 over the expression s with k appearing in it. Okay, you can in your mind quickly check that this makes sense if you take the first few summands in this expression, so k equal to 0. So we start with s index 1, then we go to k equal to 1, we have s index 2, s index 3, and so on. And with the last index n, we arrive at s index n plus 1. And here it's exactly the same. We begin with index 1, so we begin with s index 1, and the last index in the summation will be index n plus 1. So the last summoned will be s index n plus 1. So these two are the same. Now, let's get to our induction. The initial step for n equal to 0 is pretty clear. We have a plus b to the power of 0, which is 1. And then we have this sum on the other side from k equal to 0 to 0. So there's just one summoned. That summoned is a to the power of 0 minus k, but k is also 0. So it's a to the power of 0, b to the power of k, which is b to the power of 0. It's also 1. And 0 over 0 is 1. So we have just one summoned equal to 1 here, so that fits. For the induction hypothesis, we assume that there is some n greater or equal to 0 where this binomial sum formula already holds. And now in the induction step, we will prove that it also works for n plus 1 under this assumption here. So we look at a plus b to the power of n plus 1, and we can factor this into a plus b times a plus b to the power of n. And to this part, we can apply the induction hypothesis. So we can replace this expression here by the binomial sum up to n. So we have a plus b here times the binomial sum from k equal to 0 up to n. And this formula I denote with a star. And now I use different colors for the two summands here because I will compute a times this expression and b times this expression separately. So first a times this is the following. So we can move the factor a into the sum, and we get sum from k equals 0 up to n over k times a to the power of n plus 1 minus k. So the exponent of a is increased by 1 due to this factor here, and times b to the power of k, so nothing changes for the powers of b. Now I do the following. The sum starts at index 0, and I move the first summoned out of this summation, and the first summoned here is n over 0, it's just 1 with k 0, so I have n to the power of n plus 1 times b to the power of 0, so times 1. So the first summons is just a to the power of n plus 1. And then I write down the remaining sum here starting at index k equal to 1. Now I look at the expression when I multiply with b. So I take b times this expression here. And what happens here? So I move the b into the sum. And then the exponent for b is raised by 1 because I have an additional factor b in every summoned. Now I do the index shift. So because here I have an expression depending on k plus 1, and I transform it into an expression depending on k by shifting the index k upwards in the summation. What happens then? The k plus 1 becomes k, and the k's here are replaced by k minus 1. So this becomes the sum from k equal to 1 up to n plus 1 of n over k minus 1 times a to the power of n minus k minus 1 times b to the power of k. And now I do something similar to what I did here. I take out the n plus first summoned, so the last summoned in this sum here, which is just b to the power of n plus 1. Because if I plug in k equal to n plus 1 here, so the last summoned in this sum formula, I get n over n, which is 1. I get a to the power of n minus n, so a to the power of 0, which is just a factor 1, and here I get b to the power of n plus 1. Then what remains in the sum here is just the sum from index k equal to 1 up to index n of the original sum. Okay, now I have worked this out for each of the two summands individually, and now I just have to add them together. And I will use Pascal's triangle to do that. So the sum a plus b n plus to the power of n plus 1 now looks like this. So this expression star has this form here if we add this and this together. And of course I don't have enough space to work that out here, so I move it to the next slide. So this was the last equation we had on the previous slide, a plus b to the power of n plus 1 being equal to a to the power of n plus 1 plus b to the power of n plus 1 plus the two sums here. And now what we observe is both of these sums go from k equal to 1 up to n, and we have the same exponents for a and b in these two formulas here. So we can combine them together, and this becomes the sum from 1 to n over n over k plus n over k minus 1 times a to the power of n plus 1 minus k times b to the power of k. And these two here, I can write each of them in a bit more flamboyant way by writing n plus 1 over 0, which is just 1, times a to the power of n plus 1 times b to the power of 0, which is again just 1. So I multiply this twice by 1 here and here. And the same with this one. I write this as n plus 1 over n plus 1 times a to the power of 0 times b to the power of n plus 1. Now, Pascal's triangle here gives me that I can replace this one by this n plus 1 over k. And now I can combine these three terms here into a sum from k equal to 0 to n plus 1. So this becoming the summand for the index for the summation index k equal to 0, and this becoming the summand for k equal to n plus 1, and I arrive at this formula here. The sum from k equal to 0 to n plus 1 of n plus 1 over k times a to the power of n plus 1 minus k times b to the power of k. And that is precisely this binomial formula, the required formula, where I have replaced n by n plus 1. So that's exactly what we wanted to have. And so our induction is complete, and we have proved the binomial formula here. As a little exercise, you can prove something about power sets that we already know, but you can use a different proof now. So pause the videos for a few minutes and use the binomial formula you just learned to prove again the fact that the power set of a set with n elements contains 2 to the power of n elements. Okay, so if X is a finite set with n elements, then there are 2 to the power of n subsets of X. Okay, here's the solution. I hope you spent some time thinking about it. It's maybe not completely obvious how to do this. We learned in a previous exercise that X contains n over k subsets with k elements, where k runs from 0 to n. So the power sets contains all the subsets of X, and every subset of X, of course, contains between 0 and n elements. So the number of all subsets of X, or the elements in the power set of X, is the sum over all subsets with 0 elements plus all subsets with 1 element plus the number of subsets with 2 elements, and so on. So we get the sum here n over 0 for the subsets with 0 elements, which is just the empty set, so it's just 1. Then the subsets with 1 element, which just corresponds to the elements of the set X, so this is just n, plus then the next would be the number of subsets with 2 elements, and so on. Finally, we have the number of subsets with n minus 1 elements and the number of subsets with n elements, which is just the set X itself. So again, this is 1. And summing all of these up gives you the sum of all subsets in X. And this is the cardinality of the power set. And now we use the binomial formula for this, because we can think of this as being the following sum: n over 0 times 1 over n times 1 to the power of n times 1 to the power of 0. So this is just 1 written in a fancy way, plus n over 1 times 1 written in another fancy way, plus, and so on, n over n minus 1 times 1 written in yet another fancy way, plus n over n times 1 to the power of 0 times 1 to the power of n. And this is just the binomial sum formula for 1 plus 1 to the power of n. So, and this is of course 2, so this is 2 to the power of n. And that concludes the proof for this, that the cardinality of the power set equals 2 to the power of n. It's actually quite a beautiful application of the binomial sum formula. And now, a different exercise for you. Pause the video for a moment and show that for n greater or equal to 1, we have the following formula. Now we don't add the binomial coefficients just by themselves, but we add them with alternating signs. So we flip between a plus and minus sign in the sum with every other summand. So it's a sum from k equal to 0 up to n of minus 1 to the power of k times n over k. And we have to show that this equals 0. It's maybe not too difficult to believe if you recall the symmetry in the Pascal triangle. And the solution to this is again using the binomial sum formula. So this is our alternating sum, and we can write this by again multiplying every summand by 1. So this is the sum from 0 to n of n over k times 1 to the power of n minus k times minus 1 to the power of k. And yeah, this is the binomial sum formula for the sum 1 minus 1 to the power of n, but 1 minus 1 is of course 0. And if we take 0 to the power of n being greater or equal 1, then of course this is again 0. And this proves our formula here. This concludes the binomial sum formula, and now we look at another very important sum in mathematics, the so-called geometric sum, or even its infinite analog, the geometric series. And if we have a real number x different from 1 and some natural number n, then the geometric sum, this one, the sum from k equal to 0 up to n of x to the power of k equals the fraction x to the power of n plus 1 minus 1 divided by x minus 1. So it's obvious that we have to have x different from 1 for this to make sense. But of course, if x were equal to 1, then you would just be summing up over 1 n plus 1 times. So you don't really need a formula for that anyway. And we prove this with a little trick. So we multiply the left-hand side of this formula by x minus 1. And of course, our goal is to obtain the numerator on the right-hand side then. We can do that again because x is not equal to 1, so we're not multiplying by 0. And this is written out, this sum here. So it's x to the power of n plus x to the power of n minus 1 plus x plus 1 times x minus 1. And now again I look at what these two items here do when multiplied with this part. So the green bit here corresponding to the multiplication by x with this, and the red bit here corresponding to the multiplication of this by minus 1. So this becomes, if all of these are multiplied by x, then we just, for each summand, we raise the power by 1. So this is x to the power of n plus 1 plus x to the power of n plus x to the power of 1. And this is just all of this multiplied by minus 1. So we just put a negative sign in front of every summand. So minus x to the power of n minus x to the power of n minus 1 minus x to the power of 1 minus 1. Now, except for the first summand here and the last summand here, every summand here has a correspondent negative one in this bit here. So we can rewrite this sum as x to the power of n plus 1 plus x to the power of n minus x to the power of n plus, and so on, plus x minus x, and then we have minus 1 left, and so these all cancel each other out, and we're left with x to the power of n plus 1 minus 1. And now we only have to divide by x minus 1 on both sides, and we get the desired formula. So this sum here, written with a summation sign, equals this divided by x minus 1. And we're done. And a little exercise for you, just to practice your induction skills, is to prove the same formula using induction on n, but I'm not going to show that here. And another exercise, and this one is actually not so easy, so it might take some more time to complete that, is to prove the following formula. So there are n to the power of k ways of forming k tuples of element from the set xn with n elements. Okay, so here we have, xn is just any set containing n elements. If you want, think of the set of the numbers from 1 to n. And if you form k tuples out of these n elements, that corresponds to picking n elements out of this, k elements out of this set in an ordered way with repetition. So there are n to the power of k ways to do that. Now, take some time and show that the combined number of 1 tuples, 2 tuples, 3 tuples, up to k tuples of elements from this set is n times the fraction n to the power of k minus 1 divided by n minus 1. Okay, so in other words, show that the cardinality of this set equals that number. So here the powers indicate how many times you take the Cartesian product of the set xn with itself. And if you take the union of all of these Cartesian products here, then that's the combined number of all these k tuples with different, so these tuples with different number of entries, and you should prove that it equals this one. I hope you took some time to do this, and here's the solution. So the number of each of the individual tuples for a fixed number k is, as I said here, n to the power of k. So the combined number of all of these tuples from 1 up to k is n plus n to the power of 2 plus, and so on, plus n to the power of k minus 1 plus n to the power of k. Now, this should remind you of the geometric sum, because this is precisely the geometric sum minus the first term for the 0th power, so minus n to the power of 0 equal to 1. So we can rewrite this by adding 0 in the beginning, and I write 0 as minus 1 plus 1. And then with the 1 minus 1 I have here, I have indeed the geometric sum. So I have minus 1 plus the geometric sum from 0 to k. And I can replace this by the formula we just obtained before. So I have minus 1 plus n to the power of k plus 1 minus 1 divided by n minus 1. And yeah, now I bring this one to the same denominator here. So I multiply by n minus 1, and then I have this expression here. And what happens when I combine these, the minus 1 here cancels out with the minus 1 here. So I get n plus k, n to the power of k plus 1 minus n. I can factor out n here, and then I get exactly the expression that was required. If we assume that our number x, our real number x, has absolute value less than 1, then we can also look at an infinite geometric sum. So we call this the geometric series. And to do this properly, we would have to introduce the concept of a limit, which I will not do in this course. This is rather something for an analysis course. But we can get an intuitive idea of this sum if we accept some intuitive understanding of limits and convergence. And you might already have that from school or from other mathematics courses. So I will just assume that you have some idea of what limits are. And this is called the geometric series. And this infinite sum is actually defined as a limit for n to infinity of a finite geometric sum. So this is the definition of the infinite geometric series. We take the geometric sum from 0 to n, and then we take the limit of that expression here for n to infinity. This we can, by our theorem 12, replace by this formula here. So we get x to the power of n plus 1 minus 1 divided by x minus 1, and we take the limit of that for n to infinity. And here you see why we require that the absolute value of x is less than 1, because if it were larger than 1, then this x to the power of n plus 1 would just grow beyond any bound, and this limit would simply not exist, because the expression would get larger and larger and not converge to any number. Now, the theorem on the geometric series for a real number x with absolute value less than 1 is the following. The infinite sum from 0 to infinity of x to the power of k equals 1 divided by 1 minus x. And I will sketch the proof, and it's a sketch only because we haven't really discussed conversions properly. But just as I wrote before, this infinite sum is by definition the limit of the finite sums. And this is the limit of n to infinity of x to the power of n plus 1 minus 1 divided by x minus 1, because this is just the formula for the geometric sum up to n. Now, if the absolute value of x is less than 1, then x to the power of n plus 1 converges to 0 when n goes to infinity. This would require rigorous proof, so that's why it's only a sketch here, but it is easy to believe, so take some number less than 1, and if you multiply it by itself, it actually gets smaller and smaller, and so eventually it gets arbitrarily close to 0 if you just pick the exponents here large enough. So from this expression here, we then obtain the following. The limit of n to infinity of xn plus 1 minus 1 divided by x minus 1. This bit here goes to 0, so the limit is minus 1 divided by x minus 1, which of course is the same as 1 divided by 1 minus x. And that is what we wanted to show here. Yeah, and when you first encounter it, such an expression here, it may be somewhat startling to have a sum of infinitely many objects that add to a finite number, and it's not growing infinitely large. But it makes sense once you look at this formula here, once you realize you can replace these by the geometric sum, and then you see this bit here just goes to 0, and so we actually do get a proper finite limit. And let's try to understand this phenomenon a little bit better by looking at the geometric series for the value x equal to 1/2. So that's this sum here, from 0 to infinity over 1/2 to the power of k. And the limit is 2, because the limit is 1 over 1 minus x. So 1 divided by 1 minus 1/2, which is 1 divided by 1/2, and that's 2. So I begin with 0, then I add the first term for k equal to 0, which is 1. So I'm here. Now let's think of this. I'm trying to reach number 2 or even beyond by adding the summands here, infinitely many of them. The first one is 1, so I'm already halfway to my goal, to the number 2. So with all the remaining summands, I still need to get a full total of 1 to reach the number 2. But the next summand gives me 1/2, 1/2 to the power of 1. So it gives me only 1/2 of the distance I need to cover to get to the number 2. Okay, so what's left now is 1/2. But the next summand, 1/2 to the power of 2, gives me 1/4. So again, I get only half of what I require to reach the number 2. And the next summand gives me 1/8. So again, I only get half of what I need to reach 2. And we see that with each additional summand, I only get half the distance that I have to cover to reach 2. And so the summands decrease so rapidly that I will never actually reach 2 except in the limit of n to infinity. And that's actually, I think, a good way to see that no matter how far you go in the sum, you will always stay below 2, because you only, with each additional summand, only always get half of what you need to reach 2. You eventually get arbitrarily close. That's why in the limit, in the infinite sum, you have the number 2. But you cannot go past it because you never get a summand large enough to get past 2. And this geometric series actually is at the heart of a famous paradox from antiquity, or an apparent paradox, which actually turns out not to be one. And this is called Zeno's paradox. It was posed by the philosopher Zeno of Elea. And he had this little story where the mythical hero Achilles was in a foot race with a tortoise. Obviously, Achilles being faster than the tortoise. And the assumption is that both Achilles and the tortoise run at a constant speed. And the tortoise gets a head start of 1 meter. And for simplicity now, I just assume that Achilles runs twice as fast as the tortoise, which is of course not very realistic. So we assume we have a very fast tortoise here. And now Zeno's paradox was the following. When Achilles reaches the starting point of the tortoise, so after 1 meter, by that time the tortoise will have advanced another ½ meter ahead of Achilles. And when Achilles has reached that point, the 1 plus 1/2 meters, the tortoise will have advanced another 1/4 meters ahead of Achilles. And when Achilles has reached that point, by that time the tortoise will have advanced another 1/8 meters ahead of Achilles. And this goes on for infinity, and even though Achilles gets ever closer to the tortoise, he will never reach the tortoise. But of course we know that eventually Achilles will overtake the tortoise because he's twice as fast. So where's the flaw in this reasoning here? And the way I posed it, you might already have figured it out, because it's tailored exactly to fit our previous example for the geometric series. So Here we have again our length from 0 to 2, and this is the initial condition of the race. Achilles starts at 0 and the tortoise has a head start at position 1 meter. Then, once Achilles has reached the position where the tortoise started, the tortoise has already advanced another ½ meter ahead of Achilles. And once Achilles has reached this point, the tortoise is yet 1/4 of a meter ahead of him. And by the time Achilles reaches that point, the tortoise is again 1/8 of a meter ahead of him. And by Zeno's logic, the tortoise will thus always stay ahead of Achilles and he can never overtake it. Now, Zeno's mistake here was that he could not imagine adding up infinitely many time intervals together to yield a finite time period. So he thought each time Achilles covers the distance to catch up with where the tortoise was previously, that takes him a certain time. And so he added up infinitely many of these time intervals and thought, if you have infinitely many time intervals, then it has to be infinite time. And that was his reason for Achilles never being able to reach the tortoise. But in fact, these time periods only add up to a finite time period altogether in the limit to infinity, just like the distances add up to 2 eventually. So this is what happens with the geometric series, as we saw before. The infinitely many time intervals that Zeno considered got shorter so rapidly that they add up to a finite number, and of course Achilles will overtake the tortoise by the time he passes the 2 meter mark. That concludes our look at the geometric series, and finally let's have a look at different numeral systems. Of course, you're familiar with the usual decimal representation of numbers, so the decimal system that we use in everyday arithmetic. Here we say that 10, the number 10, is the basis or the radix of the representation. And what this means precisely is that we can take any number n and write it as a sequence of digits between 0 and 9, where, if we go from right to left, the digits correspond to multiples of increasing powers of 10 that contribute to n. So, for example, if we have the number 5,639, that is a shorthand for 5 times 10 to the power of 3, so 5,000. Plus 6 times 10 to the power of 2, so 600, plus 3 times 10 to the power of 1, so 30, plus 9 times 10 to the power of 0, so 9 times 1. And now we accept it as a fact that every real number, x, can be represented by an infinite sequence of digits. So we write it like that, x. Here we have the digits for the integer part of x, dk minus 1, d1, d0. So the kth index corresponding to the kth power of 10. And then we have the decimal dot, and here we have the fractional part. And there can be infinitely many digits for a real number. So d minus 1, d minus 2, d minus 3, and so on. And more conveniently written with a summation notation. So this is the sum from j equal minus infinity to k of dj times 10 to the power of j. And to justify this representation, we would have to see a construction of the real numbers, but that is not a topic for this course. So, as I said, we just accept that we can write real numbers in this way. And the number x is a rational number precisely if from some index k0 on all the digits for the lower indices are 0. So in other words, if the fractional part of the number x is only of finite length, and then eventually all further indices going further down to minus infinity, the digits are all 0. Yeah, so we have only finitely many decimal positions in such a number, and then it is a rational number. So for example here, 293.1234. So here the integer part and here the fractional part of the number. This is then 2 times 100 plus 9 times 10 plus 3 times 1 plus 1 times 1/10, 2 times 100th, 3 times 1,000th, and 4 times 1/10,000th. And this is how the decimal representation works for fractions. We can define representations of numbers for different bases b, not just b equal to 10, but in principle for any number, by just using the same principle. So let beta be a natural number, then the base beta representation of a real number x is the string of digits dk1, dk1 minus 1 down to d0, dot d minus 1, d minus 2, and so on, where all the digits dj are between 0 and beta minus 1, and the largest index here is different from 0. So we have that x is equal to the sum from j equal minus infinity up to k1 of dj times beta to the power of j. Okay, so we have exactly the same as before, only we have replaced the basis 10 by some other number beta. And again, x is a rational number if and only if from some index on all the digits are 0 for the lower indices. And if we do not use the decimal representation, so a base is different from 10, then we often write the basis explicitly as an index behind the number. So depending on what readability requires, I put the number in parentheses or not, and put the basis as an index behind it to make clear which basis we're using for the representation. And the most commonly used basis other than 10 is 2. So this is for the so-called binary representation of a number x. And here we only use the digits 0 and 1. And so this is particularly well suited for representing numbers in computers. And these digits in the binary representation are then referred to as bits. And the word bit being derived as a shorthand from binary digits. For example, the number 42 in decimal representation is represented like this in binary. So here, as I said, I write the basis 2 as an index to make clear this is a binary representation. And this is 101010 in binary. And why is that the case? Well, we decompose the number 42 into a sum of powers of the basis 2. So 42 equals 32 plus 8 plus 2, which is 1 times 2 to the power of 5, plus 0 times 2 to the power of 4, which would be 16, plus 1 times 2 to the power of 3, plus 0 times 2 to the power of 2, which would be 4, plus 1 times 2 to the power of 1, and finally 0 times 2 to the power of 0, which would be 1. And when used in computers, binary numbers are stored in units of 8 bits called bytes. So you have, of course, heard of this. And as the digits 0 and 1 can be identified with the logical truth values false and true, the arithmetic of binary numbers can very easily be implemented in computers using logic circuits, because logical operations can easily be represented in circuits by having, well, electricity on and off, a current switched on, switched off, something like that. And so you can also implement the binary arithmetic very easily in this way. that's why the binary representation is so convenient for computers. And another benefit among many is that integer division, so that is division where we just throw away the fractional part, so we ignore the remainder. So integer division and multiplication by powers of 2 can be very efficiently implemented using right shifts and left shifts of these bytes. And I write this out explicitly here to illustrate it, even though the formula looks a bit horrifying here, but it's actually very simple in principle. So let's say x is our number, an integer number represented by the bits dn down to d0 in the binary representation. And this we can write as the sum from k equal to 0 up to n of the bit k times 2 to the power of k. And then what the right shift does, it just shifts every bit here down to the next lowest power of 2. So this is we shift all the bits in this bit string here to the right, and we throw out the lowest order bit. So d0 just gets discarded. And so our bit now begins with d1 and up to dn, but yeah, this is no longer the bit for the power of n of 2, but it's now the bit for the power of n minus 1 of 2. So this is the sum from 0 to n of dk times 2 to the power of k minus 1. Okay, so we just downshifted the powers of 2, and that's the right shift. And written in a more complicated way, this is 1/2 times our original number x, where we throw out the 0th term. So we throw out the bit d0, and then we divide it by 2. And that's just the integer division of x by 2. And the left shift goes the other way, so we shift up. We shift everything to the left to a larger power of 2, and we fill up on the rightmost position with a 0. So now this is 0 times 2 to the power of 0 plus sum from 0 to n over bit k times 2 to the power of k plus 1 instead of power of k. And we can take out a factor 2 here, so this is just 2 times sum from 0 to n bit k times 2 to the power of k, and that's just our original number x here. So this is 2 times x. And what's so great about these left and right shifts, they can be implemented very efficiently in a computer. So these integer divisions and multiplications by powers of 2 can be performed very, very quickly in a computer that uses binary representation, which practically every computer does. And another numeral system of great importance in computing is the hexadecimal system. So here we use the basis beta equal to 16. And this is obviously larger than 10, and because we only have, in our usual writing, 10 digits, we in addition use the letters A, B, C, D, E, and F to denote the numbers 10 to 15 in this system. And now the advantage of this system is, because 16 is a power of 2, so it's 2 to the power of 4, we can very easily convert to and from the binary representation. And so we can use the hexadecimal representation to get a more compact representation of the bytes in a computer. So any group of 4 bits corresponds exactly to 1 hexadecimal digit. So every byte, which is 8 bits if you remember, can be written as 2 hexadecimal digits instead of 8 bits. And consecutive groups of 4 bits correspond to consecutive powers of 16. So here's a little example for that. This is a binary number consisting of 2 bytes or 16 bits. And I can write this more conveniently just with 4 hexadecimal digits. Now the colors indicate how I do this. So every group of 4 bits, I take it as a binary number and I multiply it by the corresponding power of 16. And these powers of 16 indicate the position in the hexadecimal representation, and then I just have to convert back and forth between 4-bit binary representation and single-bit hexadecimal representation. So for example, this one corresponds to the hexadecimal C, so that would be decimal number 12, and this is in fact the decimal number 12 because we have 1 times 4 plus 1 times 8 plus 0 times 2 plus 0 times 1. So that makes 12. So we have here 12 times 16 to the power of 3, and in hexadecimal that's C. And similar for the other bits or 4-bit blocks here. And to prove that you can really do that, identify every 4-bit block with 1 hexadecimal digit. You can just use the left shift for binary numbers applied in multiples of 4. So for each block here, you can think of it as having started at the first block and then shifted it 4 times to the left. And that corresponds to multiplying by 2 4 times. And multiplying by 2 4 times just means multiplying by 16. And if you do this several times, then you multiply by powers of 16. And just a remark on the notation. In technical writing, it is common to use the prefix 0x to indicate that we're using a hexadecimal representation. So what I here write as C9EA index 16 would then be written as 0x C9EA. And that concludes this video on miscellaneous topics. And in the end, I have a little task for you. Find out what the value of 0.9 is. So 0. An infinite sequence of the digit 9. And of course, you might already know that from school or from wherever. And you can write your answer and your reasoning for it in the comments to this video. And with that, I'm actually at the end of this course, Introduction to Mathematics. I thank you very much for your attention if you've made it this far. Perhaps, if I feel like it, I will make some additional videos attached to this course, but for now, I think that's enough. So if you haven't done so already, please like this video and subscribe to my channel and tell all your friends to do the same. And you will, of course, meet me in other courses I will produce on this channel.